All right, let's look at rational functions. So remember, the word rational in mathematics means there's a fraction involved. Okay, and there's two versions of this formula that we kind of think of as parent functions or as toolkit functions. But really, you can have any polynomial in the denominator. It's just that you have something with a polynomial in the denominator. Now, typically speaking, this is a polynomial divided by a polynomial, but it doesn't have to be. It can be a number over a polynomial. It can be just a single term over a polynomial, but typically speaking, we're going to have a couple of polynomials divided by each other. Okay, these functions will always have a vertical asymptote and will typically have a horizontal asymptote, and we'll talk about how to find those. Once you have those asymptotes, it's just a matter of kind of guess and checking where the pieces are going to be. Okay, and we'll talk about that too. So there's three kinds of asymptotes. We have vertical asymptotes, which you are somewhat familiar with. And this has to do with the domain of the functions. And we've done domain before, and we'll talk about how to find them. But where you put these only depends on the denominator. Okay, so the vertical asymptotes come from the denominator. You don't need anything out of the numerator for the vertical asymptotes. Functions can have as many vertical asymptotes as they want. So if I have a 10th degree polynomial in my denominator, I could have 10 different asymptotes, or I could have, smaller versions and only have 3 or something. Okay, but the idea is if I have excluded values, those become asymptotes. Okay, horizontal asymptotes and slant asymptotes. Now you will either have, and it's written down here in the third spot, you will have a horizontal or a slant asymptote. Okay, that's definitely an error. You can't have both. Okay, so there is either a horizontal asymptote or a slant asymptote. There is never both. Now, the only difference between the two is a horizontal asymptote is perfectly horizontal, and a slant asymptote is like y equals mx plus b. Okay, but typically it's just mx. So that's going to create this slanted line through there that the asymptote doesn't, or that the function doesn't go through. Now, the other weird thing about asymptotes is a function will never cross a vertical asymptote. It can't. It doesn't know how. We can't do that. However, if the x values are small, and that's a relative term, okay, we don't have like a specific number range for small, but if they're smaller, your function can absolutely pass a horizontal or a slant asymptote. But in the long run, it will go back to that asymptote. Okay, and I'll give you an example of what that looks like when we talk about them a little bit more closely. But just know horizontal and slant asymptotes are slightly different because you can cross them sometimes. Okay, so we've talked about end behavior. We're going to talk about a little more about local behavior. We've done that a little bit too. End behavior, right? As x approaches infinity or as x approaches negative infinity, where does this function go to? If you have a horizontal or a slant asymptote, the function is going to go to that asymptote at its end behavior. So if I'm looking at the end behavior here, as x approaches negative infinity, okay, so as we're moving along this part of the line, this function, notice how it goes really, really close to that positive 4. So this function approaches 4. So the only difference is now instead of approaching infinity or negative infinity, well, as instead of the function approaching infinity or negative infinity, it's approaching that horizontal asymptote. Okay, and if you want to be more specific, we could say it's approaching it's approaching 4 from the negative side. So not only is it going to 4, but it's going to the left side of, or the bottom side of 4. Okay, and I don't know if I can't remember if XYZ makes you have that minus. I just want you to know that you can have that, and it just gives us slightly more detail. Okay, as x approaches positive infinity, this function, okay, now we're over here on the right, it's coming down, it's moving out, and it moves to 4, but in this case, it's going to 4 from the top side. So from the positive numbers, it's coming back down to 4. Okay, now as we look through local behavior, okay, local behavior means what happens at the asymptotes. So at those asymptotes, and in this case, I only have one vertical asymptote, okay, so local behavior means at the x asymptotes. So any vertical asymptote should have end behavior, okay? So as x approaches, our asymptote is at positive 2, and we have to be specific here. So positive 2 from the negative side, okay? So I'm coming from the negative numbers towards positive 2, so we're looking specifically at this tail. As I approach 2 from the negative side, this function approaches negative infinity. As x approaches 2 from the right side, so now I'm going from the big positive numbers back towards 2, so we're up here, this function approaches positive infinity. Okay, so end behavior, we're talking about x going to negative infinity and positive infinity. Local behavior, we're talking about x approaching the asymptotes. And if you have 4 asymptotes, you're going to have a whole lot of notation there. I don't think they're going to do that to you, but they might, okay? Or in upper level math classes, things like that. You can have as many of those as you need. It's just a matter of finding them. You'll only have one answer for infinity, one answer for negative infinity, but those locals, you're going to have 2 for every asymptote. All right, identify the asymptotes. Asymptotes are lines. That means you have to include x equals for the vertical asymptotes, and you have to include y equals for the horizontal asymptotes, or the slant asymptotes. Okay, in this case, we have a horizontal and a vertical. So the horizontal asymptote is the bluish green one up here, and that happens at y equals 4. Your vertical asymptote is the red vertical, and that happens at positive 2. So your asymptotes are just simply lines, and they are either horizontal or vertical lines, depending on what kind of asymptote it is. All right, vertical asymptotes match the domain of the function. We'll find those in a second. Horizontal and slant asymptotes have these really weird rules, but there's an easier way to look at these rules. There's an easy way to interpret them, and you don't have to know them word for word. You just need to know situationally what it's going to look like when you get an answer in each of these scenarios, and I'll give you some examples. Okay. So, identifying the parts of rational functions. Let's take 3x squared minus 2x plus 1 over x minus 1. All right, so we start with domain. Domain is typically the simplest part because we take our excluded values. So the denominator cannot be 0. So x cannot be 1. And that tells us two things, okay? First of all, it tells us that our domain is negative infinity to 1, and then 1 to infinity. And the second thing it tells us is that I have a horizontal asymptote at x equals 1. That's the place it can't go. Okay. Your horizontal asymptotes, I wrote that wrong. This should say I have a vertical asymptote. So for horizontal asymptotes, or slant asymptotes, you're going to take the leading term from the numerator and divide it by the leading term from the denominator. Okay, and just like we did when we were looking at polynomials, the leading term is the biggest term and its coefficient. So in the top, it's 3x squared. In the bottom, it's x. So you're treating these as just kind of separate polynomials for a while. What does the polynomial on the top tell us? What does the polynomial on the bottom tell us? And we're just going to kind of pretend they're separate for a little bit. So 3x squared over x, then you simplify that. And so that becomes 3x. And since there's an x here, since there's an x in the numerator of what we simplified, that means this is actually a slant asymptote. So our slant asymptote is at y equals 3x. Okay, so now I've got a function where a vertical asymptote happens at 1, so we would sketch that vertical asymptote in. A horizontal asymptote at y equals 3x, so let's say it would look something like this. Okay. And then I just kind of need to decide, do I have any intercepts? And if I do, how do I graph them? How do I put them on here? So intercepts are the same. Your y-intercept happens when x equals 0. So f of 0 is 3 times 0 minus 2 times 0 plus 1 over 0 minus 1, which is 1 over negative 1 or negative 1. So this is going to cross at 0, negative 1, which is about here. It should be below that asymptote. I didn't draw it very well. Okay, now because that exists here, you know everything you need to know to graph this. Okay, you have a region to the left of the vertical asymptote and you have a region to the right of the vertical asymptote. Or if it helps, you have one answer for this piece of the domain, you have another answer for that piece of the domain. And within that region to the left, you have the graph can only exist above the slant asymptote or below it. Okay, it cannot be in both places, otherwise it's not a function, right? It still has to pass that vertical line test. So it's either above that or below that. Now, since I know there's a intercept right there, all I have to do is squeeze my graph into that part of it. Okay, to the left of the vertical asymptote, below the horizontal asymptote, or slant asymptote. Okay, now after the asymptote, or to the right, I just need to find a point that's over there and plug it in and see what happens. So let's say I plug in 3, and we'll say it's like right there. So f of 3 is 3 times 3 squared minus 2 times 3 plus 1 over 3 minus 1. So 3 squared is 9, 9 times 3 is 27, minus 6 plus 1 over 2, so 22 over 2, which is 11. Okay, so and that's going to be up here somewhere. We don't know exactly. I didn't put any sort of markings on my axes, and that's my fault. Okay, so that means that this function is going to squeeze itself between those two asymptotes. Okay. All right, I'm going to erase that real quick. All right, so g of x is x over x squared minus 6x plus 5. So start with your domain. Domain is the denominator. So x squared minus 6x plus 5 cannot be 0. So I need factors of 5 that add up to negative 6, which is going to be a negative 5 and a negative 1. So x minus 5 times x minus 1 cannot be 0. So that means x is 5 and x is 1. Or x cannot be 5, x cannot be 1. Okay, so I have two vertical asymptotes here. And your domain is going to be negative infinity to 1, 1 to 5, and 5 to infinity. Okay, so somewhere between negative infinity and infinity, there's two asymptotes. They happen at 1 and 5, and so we jump over 1 and 5 when we talk about the domain. Okay. So asymptote at 1, asymptote at 5. And so then we go to, what else do we need to know? Well, let's look at the horizontal asymptote. So take your leading terms, x over x squared, which becomes 1 over x. Now, if x is left in the denominator, this means that the horizontal asymptote is at y equals 0. Okay, and that's just a rule. If the variables are left in the denominator, it's at 0. Okay. So let me draw that in a different color so we can see it. Okay. Then I need to look for intercepts. So if my y-intercept is when x equals 0, then that happens at 0. Oh, that's not an F, that's a G. Okay, so my intercept is at 0, 0, which is not super helpful, right? So the difference here is that I don't have an intercept that helps me graph this. This is one of those scenarios where it's going to cross that horizontal axis for a minute, okay? And I need to know which side it's coming from. So what I've got is to just pick 3 places. Pick 3 numbers. So I'm going to choose -1. I'm going to choose something between 1 and 5, so I'm going to call it a 3. And I'm going to choose something bigger than 5, so let's say a 6. Okay. If I plug in g of -1, then I have -1 over -1 squared minus 6 times -1 plus 5, which is going to be -1 over 1 plus 6 plus 5, which is 12. Okay, so right here, it's a really small number. And what that tells me is, I know that this point is on the axis, and I know that down here it's below. So what this acts like down here is it's going to kind of have that little lump in it, and then it's going to flatten back out towards the asymptote, and it always does that. Okay, it will always come back to the asymptote. The other thing to remember is this is just a sketch. This is a guesstimate. So if it's not perfect, that's okay. We're just trying to make a good guess, right? On the other side of that, it can't go any further to the side. It has to kind of squeeze against that asymptote. And the nice thing about rational functions is that they will always squeeze to the asymptotes. Okay, so let's try the 3. So g of 3 is going to be 3. 3 squared is 9. 6 times 3 is 18. So 9 minus 18 is going to be -9 plus 5 is a -4. So I have 3 over -4, and that's going to be down here. Okay. So since I don't have any x-intercepts here, this is going to kind of squeeze itself between those two asymptotes and go through that 3, -3/4 spot. Okay. So we're making the assumption down there that everything wants to go to the asymptotes because it does. Okay. The 6. At g of 6, we've got 3 times 6 squared, which is 36, plus 2 over 36. 4 times 6 is 24, minus 5. So that's going to be a big positive number. The bottom is going to be another big positive number. And so my final answer is going to be positive. Now, the reason I only care that it's positive is because my asymptote is at 0. So it's either positive or negative on either side of that. And this one's not going to cross the asymptote. It's just going to kind of squeeze in between the two. Okay. I got to erase that one. All right, this last one I'm just going to start with the asymptotes and kind of give you a starting point. And from there, I'll let you try to graph it on your own. You can use Desmos to check your work. Okay, so let's say h of x is 3x squared plus 2 over x squared plus 4x minus 5. Okay, so domain-wise, x squared plus 4x minus 5 can't be 0. So factors of -5 that add up to 4 are x plus 5 and x minus 1. So x cannot be -5, x cannot be 1. Okay, and that means my vertical asymptotes are at -5 and +1. Okay. Horizontal asymptotes, and my domain would be -infinity to -5, -5 to 1, and 1 to infinity. Horizontal asymptotes we take our leading term from the top and our leading term from the bottom and simplify them so our x squareds cancel. And so that gives us a 3. And if you just have a number, that means your horizontal asymptote happens at y equals that number. Okay. Then you fit them in, graph them, see what you come up with, and use Desmos to check your answer. You can pause the video if you'd like, and just do all of that and then come back to this. Okay. All right, coming up with equations for rational functions. This gets a little weird, but it's not entirely impossible. Okay, you're going to start with a times a polynomial up here that comes from your x-intercepts over a polynomial down here that comes from your domain. Okay, and then we're going to use that y-intercept to kind of check our work. So the bottom asymptote, according to up here, I have an asymptote at x equals 1 and x equals 2. So that means x minus 1 and x minus 2 are part of that polynomial. Now you don't have to multiply this out. Okay, the nice thing about this section is you can just leave everything in factored form. So I have a times x, I'm sorry, putting that in the wrong spot. I'm going to have a polynomial up here. Down here I have x minus 1 and x minus 2. Okay, I have x-intercepts at -1 and -2. So if I have an intercept at -1, that means it came from a factor of x plus 1. If I have an intercept at -2, that means it came from a factor of x plus 2. So x plus 1, x plus 2. And the only thing left to figure out is what is that a value? Well, my y-intercept is 0 and 9. That means I get an answer of 9 when I plug in 0. So this is 1 times 2 over -1 times -2. So 9 is a times 2 over 2, which we know is a 1. And so that means that a is 9. So our final function is going to be 9 times x plus 1, x plus 2 over x minus 1 times x minus 2. Okay, you don't have to do a ton of work, but you do need to know, how do I find my intercepts, how do I find my domain, and how do I do that backwards? If they give you a graph and ask you the same thing, you can find all of that information. You just need to look at the graph to get it. Okay, so let's say we start the same way. I have an a value times my x-intercepts over a polynomial for my domain. So x-intercepts happen at, there's only one of them, happens at +1, which means I have a times x minus 1. Okay. On the bottom, our domain comes from the vertical asymptotes, and those happen at -3 and +3. So I have from -3, x plus 3, and from +3, x minus 3. And then I need to figure out what my a value is. And so my a value comes from the y-intercept, which happens at 0, 1. So 1 equals a times 0 minus 1 over 0 plus 3 times 0 minus 3. So 1 is -a over 9. So 9 is negative a, and a is negative 9. So our final answer would be g of x is a times x minus 1 over x plus 3 times x minus 3. Okay. All right, so here is your participation quiz. The only thing you have to do, you do not have to graph them, you do not have to find domain, you do not have to do anything except find me that horizontal or slant asymptote. If you can identify those, you're done.